Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Fabrizio Gentile with us today. Hello, Fabrizio.
Hi, everyone. Thank you so much for inviting me.
Well, thank you for agreeing to talk about your very lovely article, which we will get to in a second. And Fabrizio, what's your geolocation? Where are you at?
Currently, I'm in Bologna, in Italy. I'm completing my PhD at the University of Bologna. I'll be graduating I'm submitting the thesis actually at the end of the month.
Oh,
So I'm
awesome.
a couple of months ago away from the submission. You can imagine how busy is this period.
Yeah, well,
Uh,
it's a the time to do this. And let me be the first to congratulate you as, or maybe not the first, but at least congratulate you as Dr. Gentile. Very good.
yeah, it will be in a few months.
Very nice. And it is October 9th of 2024 as we record this, and we are past equinox. So is fall happening in Bologna or Italy, or still kind of
Yeah,
the
it
summer?
started to be actually really cold a week ago, actually. A lot of rain and fog and stuff.
Cool.
But it should be like a short period. Normally, the fall is better here. So I'm really hopeful that it will be better in a few days.
Okay, cross fingers. And I am in Phoenix, and we are still we're getting into fall, but we're still hitting triple digits Fahrenheit here in the afternoon. So it's cooling down, but we're still pretty warm. So very
I can imagine.
very nice. And Fabrizio, since you've got your thesis coming up here and all of that, what is it you like to do for research?
So, my main field of research is the evolution of galaxies. I try to understand how the galaxies evolve from the initial perturbation after the Big Bang to the celestial objects that
Hmm.
we observe nowadays.
Cool.
I think one of the most cool part of my job is that I can use data from a lot of different facilities.
Yeah.
So in the paper that I will discuss, you see that we use a plethora of different data from like the ground, the space, the new JWST, ALMA, and several other facilities. And I think it's incredibly cool to see how each facility is telling us something different about galaxies.
Exactly. Exactly. And that is going to bring us to this very awesome APJ letter. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Not so little red dots. Two massive and dusty starbursts at Z, around 5 to 7, pushing the limits of star formation discovered by JWST in the Cosmos Web Survey. And Fabrizio, take us away.
So, thank you. First of all, I would like to say that this is a collaborative effort. This is actually a job that I've been doing while I was in Austin, Texas, visiting Caitlin Casey and her group. They are all amazing people, and they taught me so much during the 6 months that I spent there. And also, this is a work that I've done with most of the collaborators that you can see listed there. They are part of the Cosmos Web collaboration.
Uh-huh.
So these amazing people managed to get a lot of observing time with JWST and to observe the cosmos field that I will discuss later. Most of the people here work on the data reduction, on the extraction of catalogs, on physical properties. So I very like honest when I say that everything that I've been doing here was not possible without the help of all the other people.
Great shout out. Great shout
So,
out.
I mean, it was mandatory to say so. I'm happy
Yeah.
that I had this moment. So, talking about science.
Okay, let's get into it.
Uh, so, in the introduction, I briefly discussed how JWST is totally changing our perspective of the high redshift universe. There are a lot of different objects that are popping out of the data. We are seeing galaxies at redshift where we were not expecting to find anything actually.
Right.
I mean, it's a very exciting period to study astrophysics now.
Indeed.
And in particular, here we are focusing on the so-called the literate dots. These are some sources that started to pop out of the JWST data after maybe during the first year of operations. They are incredibly compact sources. They are characterized by incredibly red colors. And this is actually what we know from the data.
Right.
Then everything else is from interpretation. So in the beginning, we were just thinking that these are some dusty galaxies a redshift around 9 to 10, and we were thinking that these galaxies were like really massive, around 10 to the 10th or 10 to the 11th, so are masses.
Okay.
Then, so we started to follow up all these sources, and we found out something weird. So most of these galaxies are actually hosting an active galactic nuclei.
Yeah.
We know it because we see the broad emission lines, so thousands of kilometers per second in the full width of maximum. And we are pretty sure that, it's very hard to have this kind of broad lines without the impact of an AGN. I mean, stellar population alone are not able to, even though there are some studies in the current literature that are saying that maybe it's possible, but the main interpretation is that we need an AGN.
Okay.
The problem is that these galaxies are very compact, and so we are not able to disentangle the contribution from the active galactic nucleus from the one of the host galaxy. And so when we try to understand how massive, for example, these galaxies are, we have to assign this red color or to the red emission from the AGN or from the dusty stellar populations inside the galaxy. And depending on how we are assigning this, the continuum to the AGN or to the stars, we can get very different estimates of the masses of these galaxies.
Yes.
What we try to do in this study is to say, okay, most of the ambiguity about the mass of this object is arising because these galaxies are incredibly compact, and so we are not able to disentangle the AGN contribution from the subformation. Okay. And so we decided, okay, we can try to do the same color selection, so trying to find out some very red objects, and then I will discuss how we select these objects. Okay. But now we are focusing on objects that are not compact, but they are extended. Okay. And since they are extended, we are sure that the red continuum is dominated by stellar emission and not active galactic nuclei emission.
Great.
So if we can go down.
Sure.
So we decided to look for these kind of objects in the Cosmos Web Survey. The Cosmos Web Survey is the JWST imaging of the cosmos field. The cosmos field is one of the most famous extragalactic fields in modern astronomy. The Cosmos Web Survey is covering 0.54 square degrees. So it's, a huge area for JWST capabilities at the moment. So imagine that Cosmos Web is as big as all the other public surveys conducted in the first cycles of JWST up to now. And this means that it is actually a very good area for looking for some rare objects because, we are more statistics. Cool. And in this survey, as you are highlighting there, we are just focusing on the first half of the data. They are the one that we got when we started to write this letter.
Yeah. Okay.
Yeah. So we started to look at this field and we started to select our sources. So as you can see in section 2.2, we just employed a color cut in the 2.7 micron and F444 filter. So we are selecting all the objects that are redder than 1.5 magnitudes in this color. Then since we found out that there was some contamination by fake sources or some galaxies we were not interested in, we also applied signal to noise cut in the two reddest filter of Cosmos Web. We assembled this initial sample of galaxies, and then we tried to model all these sources with point source. Okay. So we find out that most of these sources are actually compact, so they can be described as a single point spread function. And we excluded all these sources because they are the literal dots, like the actual literal dots. Right. And so, there is a collaborator, there is Hollis Akins, that is also working at the University of Texas, that wrote a recent paper in 2024, also in APJ, describing all this sample. And so if you're curious, you can go there and, take a look at the other galaxies. Yes. This is the citation. While I decided to focus on the complementary sample. So if we can skip to, I think, figure 3.
Sure, let's slide down to figure 3 and take a look at that one. So
yeah, exactly. This one here.
Figure 2?
Yeah, this one here. So we are dealing with this kind of sources. So you can see that this is the image. The second column is the image as seen in F444. Okay. There is the reddest filter in JW in Cosmos Web. We try to model this source with a point source.
Okay.
And you can see that actually, if we try to model this with a point source, we get a very bad residual. So there is the last column.
Right.
So you can see that we are just subtracting the very center of the galaxy, but most of the emission is actually extended.
Outside, yeah. Okay.
So yeah, we say, okay, these are not literate dots. We are
Yep, they are spread out a little bit.
not so literate dots or extended dots. And the idea is that, as I said before, these are incredibly red sources, but they are extended. And so the main aim of our research is to say, okay, now we are sure that the red continuum, so these red colors are due to star formation, to very dust-extincted star formation, and not to reddened AGN emission.
I'm with you.
So if we can come back up to the sample selection.
Sure, let's go sample selection, zoom out a little bit, and sample selection, and where are we at? Sample selection.
Yeah, okay. So through this sample selection, we assembled a sample of, I think, nearly 60 galaxies. I'm writing a paper on the full sample of 60 sources, so stay tuned for next updates.
Ooh,
in this letter, yeah, I mean, small advertisement. And in this letter, actually, we are just focusing on two very massive sources that we found out in this data that we are calling like object 1 and object 2.
Yes.
Yeah.
ERD1, ERD2, okay.
ERD1 and ERD2, yeah. They are incredibly red, as I said before, they're extended, and so we're trying to find out what are the physical properties of these sources. Okay. So we assembled full photometric catalogs for these sources. So as I said before, we are dealing with sources that are in the cosmos field. So we have plenty of ancillary data spanning from the radio to ALMA observation to ground-based. We have almost everything about these sources. Cool. So we put all together. I would like to highlight a couple of interesting things. That ERD1 was actually observed in a spectroscopic program with ALMA in 2019. The first author is Shu Wenjin. There is a collaborator of the Cosmos Collaboration and also friend. He was able to unveil the presence of an emission line in the ALMA spectrum, and this gave us the spectroscopic redshift or redshift around 5. So this is a very robust result because we have a spectroscopic redshift. Yeah. And also ERD1 is also radio detected. And the radio detection for this kind of sources is very important because it allows us to unveil the presence of an AGN if there is an AGN there, or in case there is not an AGN, it allows us to estimate the star formation rate in a more precise way than what we could do just with the SET fitting, since the rest frame ultraviolet radiation is not sampled by our JWST observations.
Right, I'm with you. Cool.
So we have lots of data on these sources, so we try to estimate the physical properties. And so this is where the SET fitting comes in. We use two different codes. The first one is EASY. That is one of the most famous codes, and we used it for estimating the photometric redshifts of our sources. As expected, the source that the spectrum is giving a spectroscopic redshift of 5 is also located at a photometric redshift of 5. So cool. While the other source is around redshift 7. Together with EASY, we also use a second code that is Bagpipes by Adam Karnal. And Bagpipes is a Bayesian code that is able to interpret the photometry of our sources to estimate all the physical properties. In our case, we were interested in the redshift, in the stellar mass, and in the star formation rate and dust attenuation. There are the 4 main properties that we are working on. So here in the paper, you can find all the details about the setup and this kind of stuff if you're curious. I would like to highlight the results. So if you can go down, I think there is a table. Okay, no, this is the SED fitting, figure 1.
Yeah.
So you can see that, okay, of course, we are just dealing with photometry. So our sources are, detected in 3 or 4 bands between JWST and Spitzer. An interesting thing is that ERD1, that is the galaxy with a spectroscopic redshift of 5, is also detected in MIRI, that is the mid-infrared instrument of Cosmos Web, and So we are pretty sure that, we are properly estimating the mass of this source. While for ERD2, we don't have this kind of constraint. So as I will highlight later, the stellar mass can be, a little more uncertain. Then if we go, and you can see also, that the SED fitting is quite robust. Here you can find the reduced chi-square, and you can see that it's very close to 1. So I think, that we are doing a good job in modeling the SED of our sources.
Cool.
And if you go down, in figure 2, we have some constraint about the self-formation history. Of course, the self-formation history is not that constrained, only with photometry, and this is a good reason for getting some spectroscopic follow-up of these sources. Right. But I think the most interesting thing is to go to table 1, where I show the results of the SED fitting procedure. Yeah. And you can see that, okay, we are dealing with 2 galaxies, the first one a redshift 5 and the second one a redshift 7. Okay. And if we measure the dust attenuation, you can see that all the galaxies are pretty extincted. So we have 3.8 and 3 magnitude of dust extinction. That it means that there are some dusty star-forming galaxies here. And also, if you look at the stellar mass that is estimated with bagpipes using 2 different star formation histories, you can see that we're dealing with galaxies that are extremely massive. So the stellar mass is around 10 to the 11.3 and 11.2 stellar masses. Yeah. And when we found out this result, we started to think that, these galaxies are pretty massive, considering that we are a redshift 5, redshift 7. So the universe was very young at that moment. Very active. So we knew that we were dealing with a kind of extreme source, and we were curious to find out how extreme are these sources. And I think that the main plot that is telling us how extreme are the sources is figure 4.
Let's go to figure.
Should be.
Let me zoom out here a bit, slide down to figure 4, money shot. There we go.
Yeah, this one here.
Okay.
So this is a very simple plot in the in the shape, but is a bit complicated to explain. The idea is that we know that in our universe we had the Big Bang and then the formation of structures. So we have the perturbation of the density field after the Big Bang, and so we started to have the formation of the dark matter halos. And inside the dark matter halos, we have the formation of galaxies, and so the formation of stars. Cool. The idea is that in our cosmological paradigm, we start with very small halos, and then these halos are growing up by accreting dark matter on them. And we know that normally the percentage of baryons, so actually, the baryons inside the dark matter halos, the amount of baryons inside the dark matter halos should be really small. Yes. From the cosmology, we know that a small percentage of the total amount of matter is actually made of baryons, and stars are a small fraction of the baryons. Yeah. So the main idea is that cosmology is telling us how massive the dark matter halos are as a function of the redshift, so as the cosmic time. So the lower redshift, the more massive halos we can find. Okay. What you can see here, for example, the upper line, the darker pink line, that one. Mm-hmm. That one is actually so this is the distribution function of the masses of the dark matter halos as a function of redshift. Okay. So, for example, we can see that the redshift 7, we are expecting a dark matter halo. The most massive dark matter halo should be around 10 to the 12 solar masses. Okay. Mm-hmm. So if we in this plot we are putting our stellar masses, so the stellar masses of our sources is a function of the redshift, we cannot be above this line, because above this line we have we have the amount of baryons in the stars inside our galaxies are more than the total amount of dark matter inside these halos. Right. So it's impossible. Okay. So we don't want anything beyond this line. But of course, we are not looking at the full sky. We are just looking at a small region of the sky that is the 0.28 square degrees observed by the first chunk of data of Cosmos. Uh-huh. So actually, we don't want anything above the second line, so the darker pink line. Right. Because in this case, we have something that is more massive of the most massive dark matter halo that is inside our survey. in this range of redshift.
Yes.
So again, this is too much. Then, of course, we know that, we have to convert the amount of baryons in stars. And so we have to assume a certain efficiency. So the efficiency is basically the integration of the efficiency of the star formation rate over the full history of the galaxy. And it's basically telling us what percentage of the total amount of baryons inside our dark matter halo is actually made of stars.
Okay.
So in the local universe, normally we find out that this efficiency is lower than 20%. So the 0.2 that you can see on the lower line. So basically, most of the galaxies that we observe in our universe are below this line. So they have a star formation efficiency lower than 20%.
Yes.
And this is the interesting thing. Our galaxy is above this line. Yeah. So the first one is still compatible with the 20% efficiency. There is still a very high efficiency in the local universe, but still possible. While the second galaxy is not compatible with this line, is at least 2 sigma beyond the 20% efficiency.
Right.
So what we're saying here is that if our analysis is correct, so if all our data are correct, and if our interpretation, our SCT fitting, and all the hypotheses that are behind the SCT fitting are correct, these galaxies could have a significantly higher star formation efficiency with respect to what we observe in the local universe.
Yes. Very cool.
And I think this is very cool because it's telling us a lot of different things.
Yeah.
So, or we are assuming that, the star formation efficiency in the early universe was much more efficient than what we are seeing nowadays. And this is something that is corroborated by several other studies. If you see, for example, the studies by Kathleen Casey on some very high luminous galaxies at redshift higher than 10, also published on APJ, I think, at the beginning of this year, you can see that they are finding some values of the star formation efficiency compatible with what we're finding here at redshift 5.
Okay.
And there are several other studies that are finding the same kind of results.
Very cool.
This is also very interesting because, as I said before, this is our interpretation in the case that all our hypotheses about the SCT fitting are correct. But these hypotheses are something very important in our current astronomy. So, for example, now we are assuming a certain initial mass function that is able to, to transform the light that we are observing in our galaxies into a stellar mass. All astronomers are always using the same standard universal initial mass function. Okay. But this is a strong assumption to say that the initial mass function was the same, is the same in our universe at redshift 0 and at redshift 5 or redshift 10.
Right.
There are some theoretical studies that are telling us that when the universe was very young, was much younger than what is today, and so it was very compact, and also the galaxies were less metallic, and so it was a very different environment from what we're seeing today. Maybe the initial mass function was different. And if the initial mass function is different, we can actually, lower the stellar masses of our sources. Yes. And so, to explain our results without, changing the full picture. A last thing that I would like to highlight is something, more exotic, an explanation that is more exotic. But there are actually some theoretical studies that are telling us that maybe, it's just the cosmological framework that is wrong, or maybe not completely wrong, but maybe it could be slightly different from what we are observing. Okay. So all the lines in the plot in figure 4, they are a direct derivation of the lambda CDM cosmology. So they're assuming that, the universe is around 14 giga-years old, and the dark matter halos are forming in a certain way. But if we slightly change the cosmological paradigm, for example, inserting the early dark energy or some other modifications, we can get a cosmology that is different. And so also the formation of dark matter halos we can have more massive halos earlier in time. Okay. And so again, if we have more massive halos, we have more baryons. And so the star formation efficiency can be less efficient and still get the stellar masses that we're observing in our galaxies.
Cool.
So this is what we did in this study. It's very promising. We still need, to get more data on the sources. The stellar masses that we're estimating through SCT fitting are not completely sure. So having some dynamical masses, for example, with new JWST observations, or with ALMA, and some emission lines are observable with ALMA, we would be able to constrain the dynamical mass, and so to better constrain the stellar mass of our sources. One of the two galaxies is actually only relying on a photometric redshift. So, having a spectrum, we would be able to confirm a spectroscopic redshift and to say that this galaxy is actually a redshift 7. So I think there is a lot of things to do.
Cool.
And imagine that these galaxies were just 2 of a full sample of 60 galaxies in the first half of Cosmos Web. Now we got the second chunk of data. So, will be some hundreds of galaxies to analyze, and we can see how exotic this population is actually is. So really excited about it.
Very cool. Very, very nice. Beautiful, actually. Very beautiful. Fabrizio, I want to thank you so much for walking us through your very awesome APJ letter.
Thank you for listening.
Sure. And you certainly mentioned it a couple of times there. So let me just push on it and invite you to extend the discussion a little bit. But where do you think we go from here, given the published article? You mentioned that these are just 2 out of 61, and then maybe we'll have hundreds of potential candidates here within a year or 2. Is there additional theoretical work that could be done, and so on? So just sort of next steps. Where do you think we go with these extended little red dots?
Yeah, so I will start from my small field. So what we are doing on these galaxies. So for these 2 sources, we are planning some follow-up observation. The JWST deadline is actually very close, so maybe we will try to get some additional data for them to confirm the photometric redshift of the second galaxy, and to get more information from the spectrum of these sources. As the same thing can be done for the full sample of galaxies. So we just presented these 2 sources because they were the most exciting and the most robust DSCT fitting, but they're just a small percentage of a bigger population that we want to characterize in its entirety. So a paper that I'm actually working on together with Caitlin Casey at the University of Texas and the rest of the Cosmos Web collaboration, is a paper analyzing the full population of these kind of extremely red and massive sources. Cool. So this is for my small field of view. Getting to the broader picture, I think that JWST is finding that a lot of galaxies are actually in tension with the current cosmological paradigm. As I mentioned before, Caitlin Casey showed that some redshift 10 galaxies are actually too massive for their dark matter halos. And the full, problem about the origin, the true nature of little red dots, if they're completely dominated by AGN or they are incredibly massive galaxies. It's an ongoing process. We are finding new data every week. If you check arXiv, it's full of theories and data about this elusive population of galaxies. So as a community, we are working on trying to understand what are the galaxies. And I think it's very interesting because, if they're AGN, they're too numerous for the universe. If they're galaxies, only galaxies, they're, too massive for their dark matter halos. So, we have a lot of data and we just need theories for understanding what's going on there. So, cool. As I said before, it's a very exciting period for being astronomers.
Yeah, it'll be really cool to see this develop over the next couple of years. And not only will you have a very awesome PhD thesis, but you'll probably have a very exciting postdoc. Very cool. Very nice.
Yeah.
Fabrizio, thank you so much for walking us through this very awesome article. Very nice.
Yeah, thank you again for the invitation.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.